There we go. All right, so guys, here's what we're going to do today. And literally, I think I told you to grab your old notes, right? Guys, we are going to pick up exactly where we left off. So imagine that we had just done the water flippy thing. Imagine that we just got done with this. You now understand Le Chatelier's principle. You understand that that thing is always going to return to that 7-to-3 ratio. There's nothing you can do to change that. That's all about Le Chatelier's principle. And now, guys, this is where we're going to pick up. So the conversation goes like this. So what we did last time is we did this, right? And we found out that the forward reaction had a bigger surface area and temperature, big tube, little tube, flipped everything around. Then we had the conversation about what you learned from the demonstration. You found out that, that a system at equilibrium has equal rates for the forward and reverse reaction. Just talked about that in homework. Then we talked about the idea that at equilibrium, the concentrations are not equal, but what are the concentrations? Constant, and you even remembered what these were, right? What were they from the demonstration? 70-to-30. And guys, did I even have you write that down? Is that in? And I actually wrote it down now. So guys, we talked about this ratio that was the ratio of products to reactants. It was 70-to-30, or that reduces to 7/3. And we talked about the idea that that ratio never changes. You can mess around with this equilibrium and it will always come back to that 7-to-3 ratio. You guys good with all of that? Guys, that's what we're going to talk about today, because it turns out that this 7-to-3 ratio has a name, and the name of this is what is called an equilibrium constant. And that's what we're going to talk about today. Now, guys, last time in class, did we talk about this idea that 7-to-3 is not universal for all reactions? Did we talk about the idea that you can look these up, though, in a book? Did we do? Yeah, guys, it's actually really interesting and somewhat scary. Guys, you can actually look up these product to reactant ratios for every chemical reaction known to man. They're all in here. This is called the CRC Handbook of Chemistry and Physics Constants. And in here, there are table after table after table of all of these product to reactant ratios for just about every chemical reaction on the planet. So you can actually look up these product to reactant ratios for any reaction that you would ever care to do. So these really are constants, these product to reactant ratios. And guys, the name of these, and this is where you want to start taking notes, the name of these are what are called equilibrium expressions. So guys, an equilibrium expression, and just pick up in your notes where you left off, an equilibrium expression is a mathematical ratio of products to reactants when a reaction's at equilibrium. But guys, when we talk about ratios mathematically, what kind of math are we talking about? Add, subtract, multiply, divide. Division. So guys, when we talk about a ratio, we're talking about a fraction. Just like we wrote on the board, our fraction was 70/30. Guys, that is the fraction that we're looking at. It's the fraction of products to reactants. So we write it like this. K sub C, which is actually what's called the equilibrium constant, is equal to this. Products divided by reactants. But guys, what do you remember from pH calculations? What do the brackets mean? Remember, pH is the negative log of bracket H3O. Do you remember what the brackets mean? Let me remind. How much in what units? Molarity. Guys, these are concentrations. They're molarities. But guys, now we run into a little bit of a problem. Remember that we're talking about equilibrium reactions, right? So we understand that the stuff on the left is becoming the stuff on the right. But what does the stuff on the right do? Turns back into whatever's on the left. So the problem is that these reactions go in circles. So technically, there really is not a reactant, and technically there really is not a product, because these go in circles, and so they're always reforming each other. So technically, we can't say one is a reactant and one is a product, because the products react together to make more reactant, thereby making that the product as they go in circles. So guys, what we do is this. We say that these ratios are right divided by left. And that makes sense because the products are normally on the right and the reactants are normally on the left. But we do at least need to acknowledge that the products are turning into reactants technically, so it could go both ways. So we just go right divided by left. So guys, let me show you how to write these expressions. Then we're going to do 2 of these. Holy smokes, this is going to be less than 15 minutes. We're just about done. You guys ready to go? Are you caught up with me? Okay, so guys, this is the way this works. Write this down with me. This is an acid-base reaction where hydrofluoric acid is reacting with a compound. It's called hydrogen borate, H3BO3. And guys, the products are water and HBF. But you'll notice how this balances. We've got 4 of the HFs and 3 waters. So guys, what we're going to do is we are going to write the Kc expression for this. So once you've got this written down, we are going to take this and we're going to turn it into a Kc expression. That 70 divided by 30 product by reactant ratio, we're going to write that for this reaction. So guys, what's going to go on top? This stuff or the water and the HBF? The water and the HBF, because that's what's on the right. Now guys, notice the way that this is written, because you're going to learn something here, because it's not quite as simple as you might think. The question that we need to answer is what happens to the coefficients? If this is a 4 and this is a 3, how do we deal with that? And the answer is this. Do you see it? What happens to the coefficients? They become exponents. Guys, so as you write this down, if you need to make note of that so that you don't forget, you may want to make note to yourself that when you write these Kc expressions, the coefficients become exponents. And then guys, also notice that when you write this, you're putting it in brackets, not parentheses. You're putting these in brackets because the brackets represent molarity. So to solve these, which is what we're about to do, you're going to need molarities to fill in the brackets. So guys, if you understand what you wrote down right here, you should now be able to successfully figure out what the denominator is. So give it a swing. What should the denominator look like? Look, people fiddle with this for a second and then, yeah, unless you're not going to give anything away. Oh, I forgot to mention that. Guys, did you see that as well? Guys, understand that when we write these Kc expressions, these are not additive, they're multiplicative. So you're not adding one to the other, you're multiplying one by the other. So the reason, the explanation is because that's the way we write them, but they aren't additive, they're multiplicative. And I know you're sick of hearing this, but we'll talk about why next year. For this year, you just got to be able to do them. So, but that's, I forgot to mention that. So guys, notice what Isabel picked up on, that these are not adding together, they're multiplying together. So maybe the things then in summary to keep track of is the coefficients become exponents, the additions become multiplication, and we put them in brackets. So guys, with all of that said, what does the denominator look like? Did you all come up with this? HF raised to the 4th power, and then H3BO3 not raised to a power. Notice they're multiplied together and they're all in brackets. You guys get the idea? Okay, so guys, this is what you're going to do today in homework. You are going to be given balanced equations, and from the balanced first equation, you're going to write the KC expression. Then once you've written the KC expression, one of two things is going to happen. You will either be given all of the molarities and you'll solve for KC, or you'll be given KC and all but one of the molarities and you'll solve for the molarity that you're missing. So guys, we're just going to do algebra with these. So we're going to do 2 examples and then you're going to get your homework done today. You ready to go? So guys, try this and let's see if you're doing good. So this is the reaction between sulfur dioxide and oxygen to form sulfur trioxide. Guys, scratch down the reaction really quick and then write its KC expression. Did you get it? Give me another second. Are you good? So guys, what do we do with the 2? Make it a squared. So our KC expression is going to be SO3. Don't worry about me skipping space. You'll see why in a minute. We've got SO3 in squared. And then guys, we understand the right side's on the top, left side's on the bottom. We bring down the SO2 and that's squared and then the O2. Is that okay? Okay, so now guys, this is one of the 2 types of problems that you need to be able to solve. In this problem, and don't write this down, you'll be fine without it. Guys, in this problem, you are given the final concentrations. So it says the final concentrations in this reaction at equilibrium are molar, molar, molar. So they give you the molarities of all 3 of these things, and the question is, what is the KC for this reaction? So guys, let's solve it. So in order to do that, what have we got to do? Just plug in the molarities. So guys, what is the molarity of SO3? 0.2 molar. The molarity of SO2 is 0.125 molar. The molarity of O2 is 0.11 molar. So guys, all we got to do is plug in the numbers. So what are you guys going to do to screw this up? Forget the exponents. Guys, make sure you keep track of these exponents. So this is 0.20 squared, 0.125 squared, 0.11 is not squared. So guys, make sure you keep track of the exponents. That's the common mistake that people make on these. They just accidentally drop the exponents. So now guys, the challenge becomes to trick your calculator into solving this problem. And I don't know how you've been taught to deal with squares. Some of you probably use the caret key. That's wonderful. Some of you have an x squared button. That's great too. If you really want to go old school with this, you could just go 0.2 times 0.2. That works great. I mean, if you really wanted to, you could go 0.2 times 0.2 divided by 1.25 divided by 0.125 divided by 0.11. But guys, grab your calculators, run this through, and the answer is 23. So let me give you a second to come to terms with your calculator, and you'll know that you're doing this right when you get 23. You guys, frankly, if you can't get 23, I am probably not your best resource unless you have a Casio calculator. I know Casios pretty well. Frankly, I'm on the border of helpless when it comes to these TI graphing calculators. So if you're not getting this with a TI graphing calculator, the only piece of advice I have for you is hit enter a lot. Because TI calculators are horrible with orders of operations. So I find that if you can't get a TI calculator to work, hit enter after every operation. And typically that straightens them out. If not, frankly, I'm just going to refer you to one of your classmates because you guys are better at this than I am. You guys all get 23? Exactly. But notice, 23.27. But notice 2 significant digits, so it rounds down to 23. Yep. You guys good on 23? Okay, so guys, we've got to talk about 2 things. One, did you have this experience? When you wrote down the number 23, it kind of felt wrong, kind of naked, kind of like something was missing, because I've been hammering this on you all year. What are the units? And guys, the answer is there aren't any. Finally, for once in your life, if you're the person that doesn't put units on numbers, you're actually okay. Because guys, these numbers do not have units. All of the molarities cancel out, and these numbers are what are called dimensionless numbers. They do not have units. But guys, understand this. That doesn't mean they don't have meaning, and you've got to understand what 23 means, so let's talk about it. Guys, what does this ratio represent? Check this out. What's on the top? Products or reactants? Products. What's on the bottom? Reactants. So what does it mean if this ratio turns out to be 23? That means the numerator's 23. What's on the bottom? What's understood to be there? A 1. So guys, what does that mean if the Kc is 23? Well, at equilibrium, there's 23 times more product than reactant. Does that make sense? So guys, what does that then mean? The summary is this. If you have a Kc value that's greater than 1, you have more product than reactant. You've got to understand that. Kc values greater than 1 mean you've got more product than reactant, but doesn't that make sense because products are in the numerator? Now guys, what if what if the opposite is true? What if you've got more reactant than product? Then what will your Kc value be? Smaller than 1. But guys, understand that doesn't mean negative. So guys, if you have a Kc value smaller than 1, that means that you've got more reactant than product. But guys, I'll wait for you to catch up. Tyler, are you okay? Okay. Stetson, are you good? Okay. So guys, you got to understand this though. So Kc value is greater than 1, more product. Kc value is smaller than 1, more reactant. But guys, think through this. Why can Kc never be negative? You can't have what? Yeah, you can't have negative molarities. Guys, you can't have less than none. A molarity of 0 means none, 0 concentration. You can't have less than none. So these molarities can never be negative, therefore Kc can never be negative. Kc can be bigger than 1 or smaller than 1, but realize we're not saying smaller than 0. So it's either bigger or smaller than 1. You guys good on that? Let's do one more and let's get you going on homework. So guys, starting over afresh. Hi. Get it? Hi. Yeah. That's actually called iodic acid. It's nasty stuff. So guys, when iodic acid dissociates, it breaks into hydrogen gas and iodine. It's actually kind of cool to watch because the iodine forms these really neat little purple crystals. It's kind of fun in a chemistry sort of way. So guys, write the Kc for this. Did you get it? All right, so guys, the tricky bit here is watch out for the plus sign. Remember, we don't add, we multiply. So Kc is equal to H2 times I2. And then in the denominator, we're going to have Hi squared, right? Okay, so now guys, I'm going to change the game. Instead of giving you all the molarities and having you solve for Kc, this is a little different. Don't write it down. It says if the Kc for the reaction is 0.39. So guys, let's think about that. What does that mean that the Kc is 0.39? What do you know about the equilibrium mixture? Which will there be more of? Good. Hey, right. So it's less than 1, so you're going to have more reactant. That said, so Kc is 0.39. Here's the concentration of H2, the concentration of I2. What is the concentration of HI? So let's set this up. They gave us the Kc value, 0.39. Then they gave us the molarities of the H2 and the I2. And it's asking us, what is the concentration of HI? So guys, that becomes our X. But again, what are you going to leave out? The squared. That is X squared. Guess what you get to do? Your square root button. Won't that be fun? So guys, how do we solve this for X? Well, what I like to do is multiply these together and then move the X squared over. So we end up with 0.39X squared. Do your algebra chops allow you to see that that's okay? Yeah.
So if it's so if the exponent on the bottom for HI was higher, would it just be xi like cubed or?
Could be, yeah.
If it was.
Yeah. So how do you take the cubed root on your calculator? Is that what you're thinking?
I can do it.
Yeah. What I do is caret 0.33333. But
Okay.
and then guys, 0.2 times 0.18 is 0.036. Now, how do we solve this for x? What do we do first? Divide by 0.39, and we get x squared is equal to 0.092. Now, how do we solve this for x? Take the square root, and it's 0.30 molar. What do you think? You guys okay? So what did we learn? Well, we learned that these Kc values, like from our demonstration 70 to 30, is a fixed number called a constant, which you now know you can look up in a book. Guys, then what we found out is that we can write these product to reactant ratios. You learn to use the coefficients as exponents, and as Isabel got us pointing out, don't add, multiply. And then guys, you're just plugging in numbers and doing algebra. Can you stand it? Okay, so guys, grab your homework packet. I believe that we are now on assignment 4. The answers are stuck to the wall. Good night. You've got like 45 minutes to do this. So guys, the idea here is get these done, check your answers, let me know if I can help. Oh, wait, actually, hold on. Let me stop recording and then we need to